SwayamPrabha. Digital India. Educated India.
To continue our discussion of spatial correlation coefficient, recall that I said that these correlation coefficients, 9 of them, are difficult to measure in a real non-homogeneous, non-isotropic turbulence. Usually, when measured, they are only measured in one direction, say R1. In homogeneous turbulence, as we said earlier, all statistical correlations of time average fluctuating components are 0, their gradients are 0, but gradients of mean quantities can be finite. That is the definition of homogeneous. Isotropic turbulence implies that any relation between the turbulence quantities must be constant or invariant under rotation of the coordinate system and under the reflection with respect to the coordinate system. As such, turbulence cannot be isotropic unless it was also homogeneous. So, what this means is, for a homogeneous isotropic turbulence, only R11, R22 and R33 will be finite, because all other quantities would involve spatial gradients of phi 1 dash, phi 2 dash, and therefore, they would all be 0 for I naught equal to j. And secondly, for 180 degree rotation, and let me explain this. So, let us say if I had x 1, x 2 and x 3, and let us say I am considering at some point the fluctuation u dash, and the fluctuation v dash, let us say. Now, if I turn this system through 180 degrees, so that x 2 takes this position, and therefore, x 3 would take that position. This is the negative x 2 and negative x 3, that is the turning through 180 degrees. Then in this new coordinate system x 1, x 2, x 3, you will see v dash will now appear negative. V dash will be negative in the new system. And therefore, you will see the time averaging of the product u 1 dash u 2 dash in the first system will equal u 1 dash into minus u 2 dash in the second system, and this would essentially be minus u 1 dash u 2 dash. Now, plus u 1 dash u 2 dash equal to minus u 1 dash u 2 dash can only be true if u 1 dash u 2 dash were identically 0. That is the meaning of homogeneous isotropic turbulence, and for that only R11, R22 and R33 would be finite. Further, R22 and R33 would also equal, since the coordinate system is invariant under rotation about x1 axis. That is what I showed. So, the R11 FR coefficient parallel to x1 axis is called the longitudinal coefficient, whereas coefficient R22 equal to R33 equal to GR is called the lateral coefficient. That is what I showed in the slide here. This is the lateral coefficient, this is the longitudinal coefficient. Both FR and GR decline to 0 as R tends to infinity. For a given R, FR turns out to be usually of a bigger magnitude than GR. The coefficient curves are nearly parabolic near R equal to 0, and therefore, symmetric about r equal to 0. Expanding therefore Fr and Gr in Taylor series about r equal to 0, you will see, and retaining only the first couple of terms, you will see Fr would equal 1 when r is equal to 0, minus r by what I have called Lf squared, and I will define Lf in a minute, plus additional term. Likewise, Gr would be approximately equal to 1 minus r by Lg whole squared plus several terms, where Lf square would turn out to be minus 2 times d2 f by dr square r tends to 0 raised to minus 1, and Lg square will be minus 2 d2 g dr square. These are the projections of the second derivative of f, and you will see for transfer for longitudinal correlation, the Lf would appear as that, and Lg would appear somewhere over there. That is the estimate of Lg, and this is the estimate of Lf. The Kolmogorov scales, of course, would be very, very small distance L epsilon would be somewhere here and here, but the integral scales would be of that order, because there is the integral of this curve between 0 and infinity, and likewise here. So, the Lf and Lg are somewhere between L epsilon and L integral, the two length scales which we had earlier identified. We have now identified a third length scale which is in between. These Lf and Lg are called Taylor microscales, and they are defined in this manner: 2u1 square divided by du1 dash by dx1 whole square raised to 0.5. So, you can see this has a length dimension squared raised to 0.5, and therefore, Lf, and likewise Lg will be based on u2 prime square separated by distance x in x direction. The special derivatives are very, very difficult to measure, because in a turbulent flow, to measure fluctuating velocities simultaneously at two adjoining points, it turns out to be quite a difficult task, and therefore, the gradients of fluctuations in x one direction would be quite difficult. We will see how to get over that difficulty, but before we do that, we will make some important observations. Lf and Lg, in Lf and Lg, the derivatives are difficult to measure, that is correct. Nonetheless, if this local spatial change is imagined to have been caused by the smallest scales of motion, then Lf and Lg can be regarded as the average dimensions of the range of small scale motions, because they are close to r equal to 0, and therefore, they can be considered to be range of small scale motions. Similarly, if we integrate Fr from 0 to infinity, we will get integral scales L int f and L int g, and thus we have four length scales: Lf, the microscale in longitudinal direction, microscale in the transverse direction, integral scale in the longitudinal direction, integral scale in the transverse direction in a simple homogeneous isotropic turbulence. Besides, of course, L epsilon at the smallest Kolmogorov scales, where viscosity kills turbulence and isotropy prevails. How do we estimate L epsilon? So, recall that in slide 9, I showed that Kolmogorov related L epsilon to nu cube, kinematic viscosity cube, divided by epsilon raised to 0.25. Therefore, L epsilon can only be estimated if we can estimate epsilon, the magnitude of the rate of kinetic energy dissipation. It can be estimated by noting that in isotropic turbulence, and there is a wonderful book by Heinz, it is called Turbulence, an Introduction to its Mechanism and Theory, published by McGraw-Hill in 1959, where some properties of isotropic turbulence have been given, and one of them is that du1 dash by dx1 whole square would equal du2 dash by dx2 whole square, but it would only be equal to half of du1 dash by dx2 whole square equal to du1 by 2 du2 dash by dx1 whole square, and so on and so forth. So, remember rho epsilon is actually equal to mu times 2 du1 dash by dx1 squared plus 2 du2 dash by dx2 whole squared plus 2 times du3 dash by dx3 whole squared plus du1 dash by dx2 plus du2 dash by dx1 whole squared plus du1 dash by dx3 plus du3 dash by dx1 whole squared plus du2 dash by dx3 plus du3 dash by dx2 whole squared. Now, we showed that all these will be equal in isotropic turbulence, and therefore, I have mu times, let us say 6 times du1 dash by dx2 dx1 whole square, and then du1 dash by dx1 is equal to half times du1 dash by dx2 whole square, and therefore, you will see here du1 dash by dx2 squared. This will become du1 dash by dx2 whole squared plus du2 dash by dx1 whole squared plus 2 times du1 dash by dx2 into du2 dash by dx1 as the first term, and likewise there will be second term and third term. But if I make use of this relationship, then you will see this will become 2 times du1 dash by dx1 whole squared and then du2 dash by dx1 square would again become equal to 2 times du1 dash by dx1 whole squared, and this would equal 2 times du1 by dash by dx2 will be 2 times square root into du1 dash by dx2 square, and therefore, you will see this is nothing but 2 plus 2 into 4, that is 2 plus 2 4 plus 4 is 8. So, I will get 8 times du1 dash by dx1 whole square from this. Likewise, I can show I will get 8 times du1 dash by dx1 squared from these also, and this is du. So, I get essentially 3 into, and therefore, all this will become 24 plus 6 is equal to 30 mu times 30 du1 dash by dx1 whole square. And that is what I have shown here, that rho into epsilon, remember this definition, LF is equal to 2 times u1 dash square over du1 dash by dx1 square, and that is what I have shown. So, epsilon would become essentially 15 times nu du1 dash by dx1 whole square is equal to 30 times nu u1 dash whole square by LF, and likewise 15 nu times u2 dash by LG whole square. So, this is how one estimates epsilon provided we know this quantity and this quantity, we can also estimate LF. To estimate now integral length scale, consider homogeneous pure shear flow in which the strain rate Sij of the mean velocity gradient is constant. In the turbulent kinetic energy equation, all spatial gradients of product quantities would vanish, but the mean quantities would survive, and so would this survive, but that would go to D term will go to 0, B term will go to 0, and production and dissipation would survive. Then from turbulent kinetic equation and assuming steady state, we would have minus rho u prime u j prime mean velocity gradient equal to tau dash I j du dash by dxj, which is equal to rho times rho into dissipation, and or in other words production will exactly equal to equal dissipation. This is called equilibrium state. Another way of writing this is u I j u prime j equal to S I j by 2, remember, equal to nu times, remember this is tau dash as mu times strain rate S I j. Small S I j is du I by dxj plus du j dash by dxi, whereas S I j is from the mean quantities by dxj plus duj by dxi. That is the mean Sij. So, in other words, I get ui prime uj prime time average into Sij by 2 equal to nu times small Sij divided by 2, and that is equal to epsilon, because I have divided through by density. So, you get that as a very interesting result. Now, the left hand side of this equation is associated with large scale motion ui dash Sij by 2 is really dimensionally, because ui dash uj dash is essentially v dash capital V dash squared divided by L integral, essentially large scale motion, because the mean velocity gradients are involved, and that would equal V dash cube divided by L integral. And since that is equal to epsilon, epsilon would also be equal V dash cube by L integral. This is a very important result. Remember, epsilon is associated with very small scale motion and action of viscosity, and yet it can be estimated from the representative scales of the large scale velocity fluctuation and large scale integral length scale. Therefore, this is sometimes called the first law of turbulence, that the ability to estimate epsilon ij or epsilon from large scale fluctuation velocities and integral length scale is a very welcome result, because it helps us later on in economic computation of turbulent flow, and this result is routinely used in bimodulus of turbulent flow equations. Another way of writing this same is that Sij strain rates of smallest fluctuating motion divided by the strain rates of mean motion would be V dash cube L in nu divided by V dash L in squared, and that would equal V dash L in by nu, or the turbulent Reynolds number formed from fluctuations of the mean and integral length scale. So, this is totally representative of the large scale. What it says is that, and since RET into L int is of the order of 100, it means that the strain rates of the fluctuating quantities at the smallest scales are much greater than the strain rates of the mean quantities like u, but the strain rates formed from u dash are much greater than these. Another way of saying is, we can expect therefore that in terms of amount of straining, the small scale motions are totally again uncorrelated with the large scale motion. From the results of the previous two slides, we can now estimate and compare Taylor and Kolmogorov scales. So, time scale of T f would be L f by u 1 prime, and that would equal 30 nu divided by epsilon, and under root 30 T epsilon, that would equal under root 30, because nu by epsilon is square root of is really the time scale of the Kolmogorov scales. So, it shows that the Taylor microscale time scale is under root 30 times Kolmogorov time scale in the longitudinal direction. Similarly, L f divided by L epsilon would be again that quantity. Time scale in the transverse direction would be root 15 times T epsilon. So, there is a considerable separation between time scales associated with Kolmogorov scales and the micro scales, but not as big as what we observed between integral scales and the Kolmogorov scales. So, integral and Taylor scales are related as follows. Since epsilon is v dash cube by L in cube, is equal to 15 nu times u dash square by L g, and if I take u dash as about a times v dash, then it follows that L g by L int would be a root 15 under root nu by v dash L int equal to that, where Reynolds number of turbulences of the order of 100, and therefore, T g by T integral would be under root 15 by that. In other words, the transverse microscale would be much smaller than the integral scale, and the same thing would apply also to the longitudinal time scale in comparison to integral time scale. The only difference being 15 would be replaced by 30. T epsilon by T integral, as we already observed, is Reynolds T integral raised to minus 0.5. So, in summary, we can say L epsilon is less than L f and g, and is also less than L integral, although the distance between this and this would be considerably smaller than the distance between this and this, and the separation distance, overall separation distance, would be determined by the Reynolds number. Same story applies to the time scales. The Kolmogorov time scales would be much smaller than integrals time scales, but just about small from compared to the microscales, Taylor microscales. So, now we have discovered that there are three scales, the middle one being representative. As I said, spatial correlations are very difficult to estimate, and therefore, that makes L f g very difficult to estimate. In order to do that, we undertake measurement of what is called as an autocorrelation, in which, as I said, we consider the same point, but separated by let us say this is u 1 dash at t, and this will be u 1 dash at t plus delta t, separated by time, and we would define exactly in the same fashion as we defined the spatial correlation coefficient, and this is what I show here. The value of u dash at t at the same point x k, and the value of u dash j at t plus delta t. This is essentially b I j, and u I dash squared, which is b I I, and u dash j is squared. This will be at t plus delta t, and this would be at t. Then again, if I plot values of r I j for different values of delta t, the separation time, then I would get a perfect correlation, of course, when delta t is 0, but it will go on declining as I go on increasing delta t, and beyond a certain delta t, of course, the the fluctuations at the later time would be completely uncorrelated with the fluctuation at time t equal to 0. So, like what we did earlier, I can estimate a micro time scale tau micro associated with LFG as that equal to u dash I into du I dash by dt at delta t equal to 0 raised to -1, taking advantage of the fact that the variation here is very nearly parabolic, and therefore, the projected delta t or tau micro would be that. Likewise, the integral time scale would be somewhere there, where 0 to infinity r I j d delta t. Now, we can get an idea of what should be the smallest magnitude of T max required in Reynolds averaging. In Reynolds averaging, remember phi cap average equal to 1 over T as tending to infinity 0 to infinity phi cap dt, that is what we said. And for practical engineering measurements, we would of course need the estimate of epsilon. It has to be some finite time, because we cannot go on measuring for infinite time. That estimate is now available. All it says is that from this expression we say continue for T max to be much greater than tau integral. This would ensure reasonably that phi dash bar would be equal to 1 over T max integral phi dash dt 0 to T max would be equal to 0. That is the meaning of the importance of the first importance of autocorrelation. There is also another very important thing. As I said, it is not possible to measure spatial gradients of u I dash to estimate r I j, the spatial correlation coefficient. So, the time derivatives of fluctuations at a fixed point, however, are easier to measure with a single instrument like a hot wire can enable us to measure that as a function of time. And Taylor made a hypothesis that if mean u 1 is very much greater than u 1 dash, which is usually the case, then du 1 dash by dt can be taken as minus u 1 into du 1 dash by dx 1, which gives us the estimate of du 1 dash by dx 1 required to estimate LF, the longitudinal Taylor microscale. And therefore, we can say that r 11 x 1 dx 1 would be equal to u 11 r 11 delta t dt, or in other words, L integral would be u 1 times tau integral that is given here. Now, this is a very important deduction. There are two important deductions from autocorrelation. First of all, they are much easier to measure than the spatial correlation. The autocorrelation gives you the idea of what T max should be. Usually 4 to 5 times the integral tau int is taken as in practical measurements. And then we are also now able to estimate the spatial correlation coefficient and therefore estimate the L integral from tau integral, which as I said is much easier to measure. So, my final comment on these last two lectures would be that we have shown how turbulence, once generated, sustains itself by creating fluctuations of ever smaller and smaller length and time scales. This was shown firstly by observing terms in the kinetic energy equations, secondly from transverse momentum transfer processes in a boundary layer, where we got reasonably good idea of separation between the dissipation scale or viscosity affected scales and the large scale. And then thirdly, we did the scale analysis. We have also shown that although epsilon is associated with very small scale motions, magnitude can nonetheless be estimated from large scale characteristics of large scale motion. This fact is extensively used in turbulence modeling of Rand's equations. The length and time scales of eddies are easier to measure from autocorrelation. Usually, most people measure autocorrelations and from that derive the spatial correlation coefficients. Energy from mean motion is somehow transferred down to very small scales where viscosity takes over and kills turbulence. This story we have tried to understand in physical space with physical measurements, what can be done with physical measurements. But by transforming equations in the wave number space, it is possible to elucidate this story even more convincingly. That is called spectral analysis. Although the equations generated cannot be solved in physical space unless they are brought back again in the physical space. The equations in the wave number space are difficult to solve, but nonetheless it reveals a story of what really goes on or most likely going on in sustaining turbulence. Which are the terms which actually carry out energy production, turbulent energy production? What is the role of the redistributive terms that on the cross section vanish, and what is the contribution of the dissipating motion? That story I will take up in the next lecture, where I will explain what is spectral analysis. There is also another possible explanation of this transfer process, which can actually be shown figuratively by imagining stretching and torturing of an fluid element by vorticity dynamics equations. And I will try to show you how both these actually tell the same story that we have revealed already through equations in the physical space and measuring capabilities in the physical space.